Okay. Uh, Hi, everyone. I'm Allison. I'm a poet and computer programmer, and today I'm going to take you through some threads of what I'm working on recently. I have a lot of stuff that I want to talk about, so I'm going to move really fast. This seems like it might be a crowd that can take some technical stuff, so we'll see where that goes. Um, the title of the talk is Toward a Material Poetics of Textual Waveforms, and I don't know if that's actually what the talk is about, but it sounds super impressive, so we will stick with it. One of the main threads of what I do as a poet and computer programmer is I think about interfaces for text, like how people start from language in their head and then get it into the computer. So the idea behind this thread in my practice is the fact that even though keyboards are the default text input device, they're hardly neutral, right? The shape of the QWERTY keyboard is a historical accident that reflects the materiality and the politics of its origin, and then the contemporary keyboards that we use on our mobile devices are interactive and a little bit adversarial, right? They let us do autocomplete and autocorrect, but using that technology requires its own kind of fluency. So the point of this is to say that even though we think of keyboards as being like a clear channel for our intention where we have language in our head and then it gets into our computer, they're not actually. They're these like highly mediated interfaces that have all kinds of weird things built into them. So the idea is that if we invent new interfaces for textual expression, like new ways to get language into computers, that's going to highlight the ways that the interfaces that we use are weird and then maybe open up the field for more interesting expression. This is this great quote from Amiri Baraka, which I found like only recently actually, but that kind of like summarizes why I think this kind of thing is important. I'm just going to read the whole thing because I think it's a great quote. A typewriter, why should it only make use of the tips of the fingers as contact points of flowing multi-directional creativity? If I invented a word-placing machine, an expression scriber, if you will, then I would have a kind of instrument into which I could step and sit or sprawl or hang and use not only my fingers to make words express feelings, but elbows, feet, head, behind, and all the sounds I wanted, screams, grunts, taps, itches, I'd have magnetically recorded at the same time and translated into word, or perhaps even the final expressed thought feeling would not be merely word or sheet, but itself the expression, three-dimensionable, to be touched or tasted or felt or entered or heard or carried like a speaking, singing, constantly communicating charm. A typewriter is corny. That's such a beautiful, beautiful quote. It's amazing, this idea of like moving beyond the typewriter to make something that more fully captures our ability to be expressive with language. Of course, when I call it new interfaces for textual expression, I'm referencing the field new interfaces for musical expression, and I first like sort of conceptualized this as something that I wanted to do while I was taking a class called New Interfaces for Musical Expression at ITP. And this is a great quote from Joel Ryan, who's one of the people involved in new interfaces for musical expression, that highlights the need for hands-on tools that people can use in order to get a handle on things that are previously invisible. So he says the need for hands-on and performance forces the composer to confront the abstractness of the computer head-on. Each link between performer and computer has to be invented before anything can be played. The physical relation to a model stimulates the imagination, enables the elaboration of the model using spatial and physical metaphors. It is no longer a phantom. It can be touched, navigated, and negotiated with. And this is another really powerful idea. Like, we have these like models that we use, and we have models for language, especially in artificial intelligence and machine learning. But the idea of having physical interfaces that make those models not ghostly anymore, but make them concrete, I think is a really, really interesting idea. The other thread in this is this like weird sort of mismatch in metaphor where we sort of agree that the first three kinds of practice here are kinds of performance, right? Like a dancer dances and that is the performance. The dance is the performance that the dancer brings into existence. An actor acts, a musician plays. We don't usually think of a writer as being a performer though, right? A writer might perform something that they have written, but the act of writing itself is not usually considered a kind of performance. And that's kind of weird because like the act of bringing a text into existence is itself something, it's like a weirdly like tactical, strange, kind of interesting act that feels like it should be something that you should be able to spectate, that you should be able to look at and admire while someone is in the process of doing it. So combining all of these threads, this is some pictures of my thesis work at ITP. I made all of these new interfaces for textual expression just as experiments to see how this would work. One of them that I want to talk about is called the entropic text editor. You use this like a regular text editor, except there's an extra channel of information, and it's this foot pedal. And basically, this is a video. Whoops. This is a video of what it looks like, maybe. Yeah. So there's typing here that happens, and then as you press the pedal down a little bit, it introduces randomness into the text. And randomness for this is just like messing with the kerning and maybe changing the letters randomly. It was basically the stuff that I could do easily using this, like the Cocoa text widget, which is a real awful library to try to use for text input. I don't recommend it, but it is probably the best thing to use because using web browsers for this is even worse. But you can see as I ease up on the pedal, it goes back to normal, right? So this is a new interface for textual expression that adds in this extra dimension of information and expressiveness to the text, and you end up with text like this, where you can kind of trace what the writer was doing with that pedal as you go through the text. This is Jabberwocky, of course, that this is a record of a performance of me using that interface. To create this text. And so you can kind of like reconstruct the gesture that made that. Another interface that I made is this MicroPoet 200. This is actually my final project for Dan Schiffman's ICM class. This was over 10 years ago now. And I made this, basically the idea is that you can turn these knobs. I don't know if the video of that is playing or not. I never actually did a video of me using it. I just did a video of what the output looks like. You can turn these knobs and then it modifies various aspects of the text, swapping the letters or randomizing the letters or swapping different words with the same number of pixels in them, inline and stuff like that. More recently, I made this interface called linear L system poetry, where it's stepping through a text according to an L system, a set of L system rules that you can modify, and then you can use this slider to like modify the recursiveness of that algorithm. So you can, basically the idea is that you write your rules and then you have this one expressive control that allows you to build a text. So of course, there are a lot of difficulties that make new interfaces for textual expression more difficult to make than new interfaces for musical expression. And the main reason for that, I think, is that when you're making a new musical instrument or something that manipulates audio, it's very easy to play and prototype with physical interfaces that produce continuous values. So if you have like a potentiometer that goes from 0 to 1, right? Like you can really easily think of ways to feed that into an audio synthesis algorithm as like the frequency or as the amplitude of a sine wave, as I'm showing you here. Just imagine that this is playing sound right now. It's just an animation of a sine wave, but I'm trusting you to be able to bring that to life in your head. So when you're working with audio synthesis, you're already working with things that have essentially continuous analog signals. So using a physical control with that isn't a big deal. There's like all kinds of ways to hook that up. Language, however, and specifically written language, doesn't really lend itself to continuous analog interfaces because there isn't an immediate obvious affordance between a word and a floating point value from 0 to 1, right? Like that's not something that you get for free with language. And linguistic structures, like this is a syntactic tree of a sentence, like it's really not clear how you would take a sentence in the syntactic structure and then attach a potentiometer to this, right? Like what would that even mean to be able to control this sentence with something that just like multiplied it from 0 to 1? So inventing mappings between non-literal gestures and literal output, that is an outstanding problem with this particular field of practice. So push that onto your stack for a second. I'm going to switch to the second thread in my work that I've been thinking about. And later I'm going to bring all of this together. Maybe some of you can already think, maybe some of you are thinking like, wait a second, there is a way that you can represent words with vectors that are floating point numbers. And I'm going to get to that in just a second. That's sort of what this talk is about. So the second thread of my practice is thinking about poetry as a means of exploring semantic space. Those of you who saw my talk at I/O last year, Minneapolis I/O, not Google I/O. It's confusing that those are homophones in my dialect, at least. That talk was about this idea of exploring semantic space with literal robots. So there's this quote, which again I read in, I first read in grad school. Thank you, ITP. This is from Jean Lescure, who was in the School of Oulipo. It's a French school of poetry composition, who says, "The really inspired person is never inspired, but always inspired." This sentence implied the revolutionary conception of the objectivity of literature, and from that time forward opened the ladder to all possible modes of manipulation. In short, like mathematics, literature could be explored. And I love that idea that literature can be explored, not writing literature, but exploring it, finding like new nooks and crannies inside of literature that can be mined. We can plumb the depths of literature and find new stuff hiding in there. So what I see myself doing as a poet when I'm working in this framework is I'm trying to figure out, well, what does it mean for there to be something to be explored? And so if you're thinking about literature as being something to explore, you're thinking about some kind of literature space, some kind of semantic space. And then you're building like actual literal robots that go into that space and then bring back nuggets of nonsense that we would never be able to come up with using our own brains. And of course, there are a bunch of ways of like breaking up language into a space, right? One is like color space. So this is some illustrations from a paper by anthropologist linguists who were like basically going to all the world's languages and then asking people what each of the what their words were for each of the colors in that upper left-hand corner, like the swatches of colors there, and they found that different languages basically draw different boundaries around which parts of that color spectrum belong to which color word. So we think in English, the way that we do it is obvious. There's red and there's blue and there's green and there's yellow and there's orange and there's purple. And that's just the way it is. And if it was good enough for Jesus, it's good enough for me. But it turns out that that is not the only way of doing it. There are like many, basically infinitely many ways to break up this color space, and no one way of doing that is necessarily better than another. Another way of thinking of semantic space is using timing data. This is from an experiment in 1975 that used timing data from semantic priming experiments to show that some concepts are more closely related to others by the amount of time that it takes for another concept to be primed in your brain after they mention it. There's a really interesting experiment you can do online to see this in effect. And of course, this is not like a space as it's currently mapped. It's like a direct graph with edges and nodes. But you can easily start to think about this as something like a space because it's like two-dimensional, and you can think like, well, what if we put another word in there? How far would it be from those other words? Like, why is one word closer to another, and so forth. This is another slide that I just like because it's so vibrant with like life and wonder. Some researchers did this fMRI study where they basically mapped nodes from WordNet onto the parts of the brain that were activated when that concept was presented to the person, and they drew this like actual physical semantic map of the brain, basically based on the study that they did. And who knows if this actually like works out to have any physical basis in reality, but I think it's a really interesting idea to think of like, well, we can actually like draw for each point in the brain the gradient of how much that part of the brain is activated by a particular concept. So that's another example of semantic space. Vector space models of language are another way of doing semantic space. So this is like a really simple term frequency. This is using Google Ngrams to just count basically like how many times does the word like about and above occur like right next to each other, and that's in this case 156. If you made a visualization of this, it might look something like this, where the brighter parts are where those combinations of words are more frequent, right? And then I'm zooming into it for some reason, because people like to zoom in on fields of black that have little white specks on them. I think it's universal to the human experience. This is the same thing, except it's a three-dimensional vector space model using term frequency, which again, you look at this and you're like, oh man, I'm definitely exploring semantic space. These cubes are bigger when when that particular trigram is very common. Where you don't see any cubes, that trigram is not attested in the Google Ngrams corpus. So the idea of exploring semantic space is that there are some parts of semantic space that are well known, and those are the parts of language that make sense to people. There are some parts of semantic space that we've never visited. There are all those trigrams that have never occurred before. So we can explore the semantic space by writing computer programs that produce new combinations of words or concepts or whatever to basically look into this, like, graph of word frequency and find all of these empty spots, and say, like, well, what's there? What is the bigram in that spot? Is that an interesting bigram? Why has nobody ever said that bigram before? This is a bot that I made called EveryWord. The idea of EveryWord was basically like draw a straight line through that term frequency matrix and just see what happens. See what happens when each of those words is seen in juxtaposition with the other. So two things: interfaces for textual expression and exploring semantic space. How do I combine these approaches is something that I've been thinking about a lot. What would I have to do to be able to say, like, well, I want to create something to explore semantic space, but I also want to have like live physical handles on it and make it into an expressive act that feels like you could perform it. Unfortunately for me, there is just such a thing that can help me do that, which is word embeddings. So to do that, to combine these two ideas, I need to have some way to represent the meaning of a word with a vector, with like a number of some kind. And the name in natural language processing for representing a word with a vector is a word embedding. So the word embeddings that I've been using, there are of course like many, many different ways of turning a word into a vector, and we've been turning words into numbers since like Athanasius Kircher in like 1650 came up with like a list of words and a list of numbers that you could use to do automatic translation between texts. This is nothing new. What I'm using is the word-to-vec word embeddings, where every word is represented as a 300-dimensional vector that looks kind of like this. This is the vector for the word light. So in essence, every word has a coordinate in a 300-dimensional space, right? So there's like this big semantic space to be explored that comes in the form of word-to-vec. Oh, that's where it's scrolling through, just to show you all 300 dimensions. So one of the cool things about the way that word2vec was made is that the vectors for words that have similar meanings are closer to each other than the vectors for words that have dissimilar meanings, or at least that's one way of phrasing it. So the vector for dog and the vector for puppy are the Euclidean distance, and the distance between the angles of them are less than the difference between abacus and mastodon, for example, two unrelated concepts, apparently unrelated concepts. But that's the point of being a poet, is to say, are those unrelated concepts? Let's think about an abacus and a mastodon and imagine the things that they could do together. So this is a TSNE visualization of the word-to-vec vectors for every unique word in the first chapter of Genesis in the King James Version of the Bible. I just made this because people like to look at these TSNE visualizations because it makes them feel like they can understand 300-dimensional space. So hopefully that provided a palliative for you. So the thing that I've been experimenting with lately is this idea of, well, every word has a vector, but there's also this continuous space that can be explored. So what if we just made it so you could find any arbitrary point in that word-to-vec vector space and then find the word that's closest to it? So I have this like little function that I wrote. I'm using the word-to-vec vectors from SciPy right now, but I want to expand out and maybe just train my own because the SciPy stuff isn't working out all that great. But this just basically gives me, for any given for any arbitrary 300-dimensional vector, it will return the word that's closest to that in the existing corpus of word-to-vec vectors. So here you can see, like, if I get the closest words to light, I get a bunch of words that are related to light. So using that as the basis, the idea that I'm kind of pursuing is like, well, now we have word-to-vec vectors. Those are just vectors, and with vectors we can do all of those operations that you can do on audio data with a potentiometer. Now it's kind of possible to think about doing that with language data, because now we do actually have this this like floating point number or combination of floating point numbers that represent a word. So all of that stuff that you can do easily with audio data or even image data, you can now do to language data. So maybe we can do that. We can do some experiments in exploring the space and some experiments in manipulating the space. So I want to show you some of these experiments. The very, very first thing, or not the first thing that I want to talk about, this wasn't the first thing that I tried, is just like finding absolutely random points in the word-to-vec space and then seeing what words come closest to it. So I found the mean and standard deviation of every dimension in my word-to-vec corpus, and then I made a function that basically like generates a random value with Gaussian distribution. And you can see there that if you ask it for 5 random words, it gives you 5 random words. This is a TSNE visualization of a 25-word poem, which I like a lot. Flawless Horses, Adobe Chanteuse, Dickens, Christchurch, Wolfenstein, Almaz, Ip, Unaria, Leichhardt, Olita, Aleph, Czech, Key Boutique, 400 meters, Peshawar, Coiled, Modernist, Thorax, Ribbon-cutting Saturn, Polyclinic Moderns. This is pretty great. I was very encouraged by these results. The next thing that I tried was JPEG compression on this data. So I just barely figured out how JPEG compression works, even though I've been a computer programmer for a really long time. It only recently clicked. I just sort of one day like looked it up on Wikipedia and was like, I have somehow learned by osmosis everything that I need to know in order to kind of understand the basics of JPEG compression. It was like amazing. It was like all of that money on grad school was well spent because I can have this moment of understanding JPEG compression. So JPEG compression, I will review it very briefly. You can have any random sequence of numbers. This is just a sequence of 25 numbers or so that I've graphed here in NumPy. This is using a random walk just to make it a bit more interesting than totally random numbers. You can do an operation called a discrete cosine transform. A discrete cosine transform basically posits that you can represent any sequence of numbers as instead the sum of a series of cosine functions at different frequencies. So this is the DCT transform of that original data, and then this is the graph of the waveforms that correspond to the frequencies. If you add all of these waveforms together, you will get the original data. So I have like an animation here that basically shows like, oh no, did it skip the animation? Yeah, that is not the animation though. Here's the animation. That's showing basically as you add, you can start with the lowest frequency waveforms, and as you add those as you add in the higher frequency waveforms, it gradually comes to approximate the original values better. The idea behind JPEG compression is like, well, with only like half of those coefficients, it's still good enough, right? So if we only store half of the coefficients for this data, we can basically only store half of the data because the coefficients take up the same space as the original data and get something that's basically good enough. So this is the idea behind lossy compression. So as long as you're okay with being a little bit inaccurate, then you can represent the data with like fewer things. So this is like the original data, the DCT of that data, and then the truncated DCT, which you can include like just one of those or like up to all of them, but you can basically control how many you want to store, and that lets you store the data with fewer items. So with JPEG, it's using 2-dimensional cosine functions instead of 1-dimensional cosine functions. This is a really beautiful graphic from Wikipedia, which I'm including here because it's like a really great illustration of this concept, just showing like the increasing frequency waveforms being added over the previous ones to approximate the original data. So because word-to-vec vectors are just vectors, you can also use DCT data on this as well. So basically what I experimented with was lossy text compression, like taking text, finding the waveform that represents the word-to-vec vectors in that text, and then reconstructing the text after cutting off a certain amount of those coefficients. So let's get to the animation for this maybe. So here's at 100%, or this is actually at 91% compression, and it's still pretty good. And the cool thing about word-to-vec data is that the text, even when it's lossily compressed, still seems to maintain some of the meaning, right? Because the word-to-vec vectors are closest to the vectors that mean similar things. Once you get down to, this is 99.7% compression, in which case this is the first verse of, or the first chapter of Genesis from the King James Version of the Bible. It's basically, compressed down the Bible to just the words measuring and diary, which is actually an amazingly poetic summary of the first chapter of Genesis. So here's an animation that shows that entire process. Showing you the text getting more and more transformed. So this again is like a textual procedure using this continuous semantic space, and this is basically you could control this process with a potentiometer, right? Because you're just increasing the text compression rate from 0 up to 100, and it's changing the text along the way. So a physical handle on the phantom model. The next thing that I tried was Gaussian blur, which you can also do with word-to-vec data. We're used to using Gaussian blur for images, like it basically just, takes each pixel and then does an average of the surrounding pixels to like really simplify that process. But you can also use this on like a matrix of arbitrary dimensions. It doesn't have to be a 2-dimensional array of pixels. It could be a 1-dimensional array of 300-dimensional matrices. So here's another animation. This is Gaussian blurring the first chapter of Genesis. And you can see that it basically ends up doing the same thing as the text compression, or as the lossy text compression. But the thing that I did with this is that I actually like attached this MIDI controller to it, and this is manipulating Jane Austen. So I'm like actually coming through on the on this promise of trying to get something close to Amiri Baraka's expression scriber with this particular technique. I have a number of other prototypes in the works that are sort of similar to this. Some things that I need to work on right now, I'm just using like cosine distance between the actual numbers and the vector, and I think that's probably not the right way to do this. Probably be better to use some other measure of distance between the vectors. I'm also finding that word2vec isn't continuous in the way that I want, in that like just taking 2 vectors and then finding the midpoint of those vectors doesn't usually result in something else. Like you can't find a word that's halfway between 2 vectors just by finding their midpoint. Ideally, I would like to be able to do that, because then the way that I'm conceptualizing this would like completely work the way that I want it to. So maybe that's a matter of just word2vec not being the right word embedding, or maybe I need to use some other like technique of thinking about it. Maybe that's tied up in the measures of distance. And then finally, like most of the stuff that I've tried so far, it just feels like it's creating text with the same texture. It would be great to be able to make these procedures feel like they're doing something different other than just like, well, when the slider's all the way down, it makes sense. When it's all the way up, it doesn't make sense, and you can kind of adjust it between sense and nonsense. There's potential for it to be more expressive than that, and that's what I'm looking for. So that is all I have. I want to thank the DBRS Innovation Lab, because they've been paying me for a month to basically work on this stuff that has no obvious practical use. So they're doing a real good thing for me personally, and hopefully for you, because you got to see this talk. Thank you. Do we need to move on, or is there time for questions? Okay, maybe 1 or 2 questions if there are questions. Or not? Sure.
Did you use the embeddings for like Wikipedia, or did you make your own from the first chapter?
They're whatever ones come with SciPy, or not SciPy, with Spacey. Yeah.
So the original word2vec and glove embeddings have Wikipedia, so you could try that and see if it's less sparse.
Right. I think the next thing that I'm going to try is just training my own on like one corpus, because I think that that'll produce results that are that feel a little bit more unified.
I think it'll be less good because it'll be sparser.
Yeah,
So
well, that's the other question.
You want as much data as you can from as big a corpus as you can get,
right,
to fill in gaps, is my intuition.
Right.
Because when I did it on just Jane Austen, it was a lot sparser than.
Yeah, but I like the Jane Austen results because like it felt like it was conceptually unified, even if it wasn't necessarily.
No, that's the trade-off.
Yeah. So, let's go over here.
You do you have any interest in generating new words in the sense of can you generate a word that's between two vectors of words that exist to find a new word that somehow bridges the gap between?
You mean like just inventing the new word?
Yeah. Is that
Yeah, sure. That sounds like a cool thing. Like, just point at that point in vector space and say like, this is schmla.
Yeah.
Yay, schmla. Okay, last one.
What would happen if you took a potentiometer and just had to control like one floating point out of the 300 dimensions? Does that have any meaning to us at all?
I haven't tried that yet, but I wanna see what happens with that. Just like being able to basically just draw a straight line through the space. And I showed you just like picking random values, but I think also doing like a random walk where it's like, you know, doing Brownian motion through all of the vectors might also produce something interesting. So, thank you.